Hello everyone, this is Rui PCB, your trusted PCB partner. Today my topic is the impact of vias on four-layer boards and an analysis of process parameters. In multi-layer PCBs, vias serve as bridges connecting different signals. But have you ever considered that these seemingly simple holes could actually become obstacles in high-speed signal transmission? Today, we will take an in-depth look at the calculation parameters of vias and how they can silently affect our high-speed machines. For example, in this board, there are many vias, each serving different functions. In our layer diagram, you can easily see that all these black holes are vias. We are already very familiar with this. Whether it's a double layer board or a four-layer board, vias are very common. So what exactly is a via and why is it so important in multi-layer boards? A PCB via is a metallized hole on a PCB used to connect conductive patterns on different layers, such as traces, pads, and planes. It typically consists of a pad surrounding the hole on each layer and the plating inside the hole itself. What role does it play in multi-layer boards? First of all, it enables interlayer connection. This is the fundamental function of vias. The space for components on a multi-layer board is limited, so vias are needed to switch signals between different layers to achieve complex component layouts. Another function is to connect many densely packed components. Vias are used to connect to internal layers. This is commonly seen in BGA, ball grid array packages, because BGAs have a large number of pads, and many of the pads in the middle cannot all be routed out directly. Therefore, vias are needed to lead those signals down to the inner signal layers for routing. So what types of vias are there? You can take a look at this diagram. We'll see you next time. There are mainly three types. The one on the far left is called a through-hole via. It penetrates the entire PCB, going from the top layer to the bottom layer, passing through all the layers. This is called a through-hole via. Then the blind via is on the right. It connects from the outer layer to an inner layer, but does not go through the entire PCB. For example, on this four-layer board, it only connects between the top layer and the R2 layer, so it's called a blind via. The one in the middle is called a buried via, which connects two internal layers and is not exposed to the outside. Blind and buried vias are generally used in special cases, such as when space is limited, or sometimes to prevent others from copying the board. Some blind vias are also used. In four-layer boards, through-hole vias are the most commonly used. Basically, we've always used through-hole vias and haven't used blind or buried vias yet. However, for more complex board designs, blind and buried vias might be introduced to save time. How do vias introduce parasitic inductance and parasitic capacitance? Although vias may look very small, due to their physical structure, they exhibit significant parasitic effects at high frequencies. The first is parasitic inductance. How is parasitic inductance generated? Any current passing through a via will create a current loop formed by the metallized wall of the via and its return path. When high-speed signal current flows through the via, this loop generates parasitic inductance, which is formed between the via wall and some copper layers above, such as power or ground. So what impact does this have? Inductance resists changes in current. At high frequencies, the impedance caused by parasitic inductance becomes significant. This means that vias exhibit high impedance at high frequencies, leading to signal transmission loss, possible voltage drops, and ringing. Imagine it like water flowing through a narrow and winding pipe. It will create significant turbulence. The same goes for current. When current flows from the upper layer and then suddenly passes through such a small via and its barrel before transitioning to other layers, this acts as a small but high impedance obstacle. As for the parasitic capacitance of the via, its formation mechanism is that there is a dielectric between the wall of the via and the surrounding reference planes, such as the ground plane and power plane. This is similar to two parallel conductive plates forming a parasitic capacitance. The wall of the via will form capacitance with those planes it is not connected to. A parasitic capacitance is generated between the via wall and these planes because there is no direct connection between them, only the PCB material in between. The effect of this is that the parasitic capacitance acts as a path for charge. At high frequencies, the combined effect of these parasitic capacitances becomes significant, diverting part of the signal, much like a small bubble constantly drawing off some water from a flowing stream, which leads to signal attenuation and loss of signal integrity. Let's take a look at the parasitic capacitance and parasitic inductance of a via. This diagram shows the parasitic capacitance and parasitic inductance of a via. The middle part represents the via itself, while the darker areas on both sides represent other layers, such as ground or power. During signal transmission, there is parasitic inductance along the path and parasitic capacitance between the via and its surroundings. This is equivalent to having many small capacitors here, which absorb part of the signal as it passes through. Additionally, there is a resonance effect. The parasitic capacitance and parasitic inductance together form an LC resonant circuit. When the signal frequency approaches this resonant frequency, the impedance changes dramatically, causing severe signal distortion. As shown in this diagram, it forms an RC equivalent circuit. If the transmitted signal happens to fall within this frequency range, it will be significantly affected, resulting in severe signal distortion. What negative effects do these calculated parameters have on high-speed signal? First, signal reflection. The discontinuity introduced by vias and traces causes signal reflection, leading to waveform distortion such as overshoot, undershoot, and ringing. Signal attenuation and crosstalk. Parasitic inductance and parasitic capacitance increase at high frequencies, which will increase signal loss and reduce signal integrity. Third, increased delay. Vias cause additional transmission time delay for signals. Fourth, worsened crosstalk. The electric field of the via can spread to surrounding areas, increasing crosstalk with adjacent signal lines. Fifth, power integrity issues. If the power or ground lines are connected through vias, their parasitic inductance can affect the overall performance of the power supply. Today, we learned about the structure of vias and how they introduce parasitic inductance and parasitic capacitance. We also learned that these parasitic parameters can have negative effects on high-speed signal transmission, such as causing reflection, signal degradation, and loss. Recognizing these issues is the first step in optimizing via performance during testing. In the next lesson, we will delve deeper into specific strategies and optimizations in PCB design to minimize these parasitic effects as much as possible. If you enjoyed this video, please subscribe to my channel for more content. Thank you, everyone.